So, start this recording here. Okay. We said last day, right? We finished 1.5, but then 1.7, I'm just going to leave because it's just word problems. But then I also promise that even though you might have to do a couple of word problems on the assignments, right? That's okay because you've got time. You can kind of ask me questions and you've got time to figure it out. But on the tests, there will be no word problems, right? It'll just be math. Right? Do this, do that, do this, do that. Right? And so today we're going to start 1.8 on inequalities. Oh, and just a heads up, next Friday, I won't be able to be here. So Jenna's going to come have you guys. She teaches the other section, so it'll be her second run through. So she'll be a machine, right? And so she's teaching pre-calc as well, just the other section and or another section. This week though, she's been really, really sick. So now I'm kind of worried that she's still going to be sick next Friday. Make sure that you were able to get that announcement. When I sent out that announcement on Moodle, make sure that you got that. And because if I'm not able to be here and she's not able to be here, I don't have anyone else. So, so then class would be canceled. But I'll let you guys know, and I'll mention it again on Tuesday. But yeah, so there goes my perfect plan. Because I covered for this week, so I was like, oh, can you do my Friday next week? So hopefully, we'll see. Hopefully she gets better. All right. Any questions, comments before we start here? Okay. So we're going to start 1.8, which is inequalities. We've seen a couple of inequalities, I feel like, earlier, right, where we just had to graph them on a number line and things like that. Now we're going to learn how to kind of do math with inequalities, right? So inequalities are things like less than, greater than, less than or equal to, greater than or equal to, right? And so an inequality, so this is less than, greater than, less than or equal to, and we know these. Less than or equal to, greater than or equal to. When I went to school, they were always like, oh no, the alligator eats the big one. But for some reason, I could never wrap my head around, okay, so if I'm the alligator, then this is the bigger one, but then I had a hard time, I don't know, I just had a hard time kind of mapping that back to less than or greater than. And so then a couple of years ago, I had a student who said, well, you just make an L with your hand. Right, this is not an L, this is an L. And then here, if it makes an L here, then it's less than. And I find that that's a lot easier because then you can read it as A is less than B, right? And so it's just a lot, I find it's a lot more intuitive if you just use the kind of your less than, well, this is not an L, so it's greater than. Right? So, just want to let you guys have that one. And if you've got your inequalities down, that's great. Nice, right? Okay. Inequalities, instead of one solution, right, to an inequality, there's going to be many solutions, right, because we want all the x's less than some number, for example. Right, so that's the difference, but in general, we can treat an inequality as if it's an equal sign, right? And so we can solve equations. We know how to move things around the equal sign. You can move things around the inequality as well, right? And so for the most part, and I'm going to underline this in red because it's not always the case, and we'll really talk about the cases when it's not true, right? But for the most part, we can solve inequalities by treating it as an equal sign. By treating it as an equal sign. Right. So you can move things around. Right. Let's think about a true statement, something that we know is true. 2 is less than 4. Right. If I add 2 to both, or add 1 to both sides, that statement is still true, right? What if I multiply both sides by -1, for example, right? -2 is not less than -4, right? And so if we multiply by a negative number or divide by a negative number, the sign, we have to switch the sign, right? And so notice, oops. Notice that if we have -1 times 2, and then -1 times 4, brackets around both -1s, then -2 is greater than -4, right? If you think about on a number line, at 0, -2 is greater than -4, right? So here, if I write it in red, is that too obnoxious? Maybe. How about in green? If we multiply or divide both sides of an inequality, by a negative number, we must switch the inequality. We must switch the inequality. Otherwise, it won't be true anymore. That's one thing that we have to keep in mind. That's the main thing. If you go to your 1.8 notes, and where are we here? Here are the rules, all the rules. But these can be kind of tricky to read sometimes, right? Kind of boring. Here, this situation is going to be less common. I don't know if I can, I don't know if the lights, I don't know, it's so glary here. Is that better or worse? Better, right? It's just so bright here. Nice. So here, what we said earlier, right? If C is greater than 0, so if it's a positive number, then if A is less than or equal to B, then we can rewrite it as, we can just keep the inequality the way it is, right? And then the one that we just showed was property number 4, right? But I think it's easier to just say it in words, right? If we're multiplying or dividing by a negative number, we have to switch the inequality, right? But that's what number 4 says. The other time that we have to switch the inequality is if we take the reciprocal. This isn't going to happen very often, right? But if you've got 2 is less than 4, and then you do 1 over 2, that's not less than 1 over 4, right? And so taking reciprocals is the other situation. But it's less common that we actually take the reciprocals of inequalities, right? So it's not, and I think you'll see it, right? It'll be easier to see it. The other time, or the other instance, where we must switch the inequality is if we take the reciprocal of both sides. If we take the reciprocal of both sides. Right. Using that example, 2 is less than 4, right? But 1 over 2 is greater than 1 over 4, right? A half is greater than a quarter. And so this is from property number 5 up here. So how about we do some examples then? Let's see here. Copy. Let's start off with one like, I don't know, which one? 21? 21. Let's do it. You guys have the answers to the odd or the evens? I was thinking I should do the ones that you don't have the answers to. Yeah, it's confusing because this one has all of them. So that's why I brought it, because I realized it has all of the answers. So if you're working on something and you're not sure, then you can flip through this one and have a look at all the answers. Yeah, I can't remember which one. Confusing because I have all of them. But anyways, let us do 21 by request. We'll start with 21. So if we have something like 4x minus 7 is less than 8 plus 9x, if we're solving this inequality, right, we want to solve for x, right? We want to get x on one side and all the numbers on the other side. Right? And so treating the less than sign as an equal sign, right? Keeping in mind, if you end up multiplying or dividing by negative, you have to switch the sign. Give that one a go for a couple of minutes here. Not too long ago. I'm talking all day. So. Okay. So just like if it was an equal sign, right, we're going to start shifting all the x things over to one side and all the number things over to another side. And so I like to have my x on the left. So I'm going to move my x's to the left. And so what I get is I get 4x minus 9x, subtracting is safe, right, is less than 8 plus 7. Right? Just kind of showing what I did, because I did pull a fast one here. This one over here, and this one over here. But now I can collect like terms, and so I get 4 minus 9, I'm pretty sure is negative 5x, is less than 8 plus 7 is what, 15? Nice. I've got negative 5 that I have to divide over, right? But we have to be careful because now we're dividing by a negative number, right? And so I have to flip the sign. And so I can say that x is greater than 15 over negative 5. No, just the negatives. Just the negatives mess it up. Yeah. Positives are fine. But negatives are bad. They're not bad, but we have to flip the sign. Yeah. Exactly, yeah. So multiplying or dividing by negatives, that's when you have to flip them. So 15 divided by negative 5, x must be greater than negative 3. Oops. Clean that up. We've sort of been writing stuff in interval notation. What would this look like in interval notation? If x has to be greater than negative 3, right, then we would have negative 3 up to infinity. But because it's not including negative 3, it's just greater than negative 3. So all values greater than negative 3 are solutions. And so the solutions would be the interval from negative 3 to infinity, but round brackets, right? So here, round bracket for greater than or less than, right? And square brackets, we use square brackets for negative 3 to infinity, for example, for x greater than or equal to negative 3.
What about for set notation? Would that be for all values of x such that x is greater than negative 3?
Yeah. Okay. So for set notation, you might have something like this, x such that x is greater than negative 3. Something like that.
Why is it only square brackets on one side?
So if we're talking about infinity as one of our things, we always have a round bracket on infinity. And so, because infinity is not a number, infinity is an idea, right? Because once you feel like you've reached infinity, you can always go further, right? And so that's why we have to have round brackets on infinity. And that's a rule that we just stick with. Nice. Cool. All right. Should we do 36 maybe? 36 is pretty big. Fractions. 2 inequalities. Let's see if I can copy it here. Negative 1/2 less than or equal to 4 minus 3x over 5 less than or equal to 1/4. So again, we want to get x on its own, but in this case, right, we've got two inequalities. So what we're going to work towards is just having x here in the middle. And so you're allowed to move this 5 out from the middle. Sorry, I can't see you guys. You're allowed to move it out, but it has to move out to both sides, right? So you'd have to multiply both sides by 5 to get it out from in the middle. So give that a little try before we do it together.
Would you tell me to think the same? 4 minus 3x
Say that again, sir.
4 minus 3x to be in the same, you have not to really multiply by 5?
Well, technically, we're multiplying everything, every item in here by 5, right? But if we multiply this by 5, we've got 5 times all of this, which would cancel, and so that's how we're moving it out. But yeah, so it would just, we would be left with 4 minus 3x. So if we start this, I'm trying to get x on its own in the middle. And so first thing I'm going to have to do is multiply all the items by 5, right, to get that 5 in the middle to cancel. And so I get negative 1/2 times 5 is less than or equal to, and maybe I'll show, actually, you can use a dot for the multiple or brackets, it doesn't matter. Maybe I'll show the multiplying by 5 over here. So times is less than or equal to 4 minus 3x over 5, and then all times 5 is less than or equal to 1 over 4 times 5. 5 cancel. So we can rewrite this as negative 5 over 2 is less than or equal to 4 minus 3x, which is less than or equal to 5 over 4. Next thing I want to do is I'm trying to shake out my x, right? But first I have to subtract 4 from every phase in this interval, right? And so I get negative 5 over 2 minus 4 is less than or equal to 4 minus 3x minus 4 is less than or equal to 5 over 4 minus 4. Showing that those are going to cancel. And you don't have to show, you don't have to write the times 5 and minus 4 in the middle if you don't want to, right? I'm just showing what we're doing. To simplify this, right, negative 5 over 2 minus 4, we have to, if we want to rewrite it as one fraction, right, we have to get 4 over the common denominator of 2. So we get negative 5 over 2 minus 4. And then I just use my usual trick of times 2 over 2 because I want it over 2. I can multiply by 1. It's less than or equal to negative 3x, which is less than or equal to 5 over 4 minus 4 times 4 over 4.
Why we split the whole of each of the statement not add the 4?
Because in order to get rid of this 4, is that the one you mean, or do you mean this 4?
Yeah. No, this one. That.
This one?
Yeah.
So in order to move this outside, right, I had to subtract 4 from all the things, right? So I have to subtract 4, subtract 4, and subtract 4. And so to move it outside, we have to subtract 4. Good. So then from here, right, I can rewrite this side as negative 5 over 2 minus 4 times 2 is 8 over 2. It's less than or equal to negative 3x is less than or equal to 5 over 4 minus 4 times 4, which is 16 over 4. Right. But whatever trick you're comfortable with to find that common denominator is fine by me, right? If you're fine with or if you're okay to use the lowest common denominator, if that works for you, then that's great. If you can just look at 4 and say, well, I can rewrite 4 as 16 over 4, then that's fine too. Yeah. Yeah, usually we kind of float it to the top. But it actually won't, it wouldn't matter. You can keep writing it on the bottom, but just so, I think it's so that we see it right away. I tend to float it to the top. Yeah. Yeah, so here, this one, for example, right? If you're multiplying fractions, then you can just multiply across, right? 4, you can technically write as 4 divided by 1. So 4 times 2 over 1 times 2 makes 8 over 2. So now we can combine these because we've got the common denominator. And so we've got negative 5 minus 8. Go with 13. So negative 13 divided by 2 is less than or equal to negative 3x less than or equal to 5 minus 16. I'm going to go with 11, but just to make sure. Negative 11 divided by 4. We're so close to having solved for x, right? But we do have to keep in mind that here, to move this negative 3 out, I have to divide everything by negative 3, right? And so I have to divide by negative 3, which means I have to switch my inequality both times, right? And so I've got negative 13 over 2. Here's where I'm going to get sneaky, times, you know what, 1 over negative 3. Or should I do it properly? This way or that way? Or which way? The other way would be to rewrite this as negative 13 over 2 divided by negative 3. Technically, negative 3 can be written as negative 3 over 1. Now I've got a fraction over a fraction.
Well, you have to, I mean, you have to convert it to that anyway.
Yeah. So I skipped a step. But as a rule, because that's how it behaves, right? If we've got -3 up top here and I want to divide this over here, we can just skip straight to this step, right? Because it'll always behave that way. So I think I'll keep it the way it is there. Making sure that I switch the inequality. Times -3x times 1 over -3 greater than or equal to -11 over 4 times 1 over -3. You can always check, right? If as long as you're doing it to the middle thing and it's getting rid of what you want and how you want it, right? Then you're allowed to do that, and that's what you should be doing, right? So that's why it's nice to kind of see what it looks like in the middle as you're solving for x. Because now this -3 and this -3 would cancel. I'm going to get a negative over a negative. It's going to make a positive, right? And so what we get here is we have 13 over 6, because we're multiplying fractions, is greater than or equal to x, which is greater than or equal to -11 over -12 makes 11 over 12. Nice. I will highlight that I switched the inequality here. Usually, we write intervals from the smallest value to the highest value. So what I'm going to do is I'm just going to rewrite this way, right? Making sure that the inequalities still stay true. And so we usually write intervals as a is less than or equal to x, which is less than or equal to b, right? Something like that. So we say that in our case, x is less than or equal to 13 over 6, or sorry, yeah, and greater than or equal to 11 over. In interval notation, right, if we had to convert this to interval notation, we've got square brackets, right, because it's less than or equal to, greater than or equal to, and so our square brackets would be from 11 over 12 up to 13 over 6. Cool. Now, I didn't try this beforehand, so it could really backfire, but hopefully it doesn't. In section 11, it's just going through and showing you how we can solve things algebraically like this, right, that we just did, or graphically we can solve it. It's just a method of checking your work, really, right? And so what I want to do is I just want to introduce checking all your work on Desmos, right? So remember, I told you about Desmos, I'm pretty sure, right? It's this free app that we can have. It looks like this little guy down here, and I'll start fresh here. But so you don't even have to sign up or anything. You can just download the app and play around with it. And it's actually really impressive what it can do. So it's pretty cool. And so notice that it has the less than, greater than, less than or equal to. Even if you need more functions, right, you can go in here if you need things like sine and cosine, right? So it's got a lot of options on X, Y. So what I'm gonna do is, and here's where I'm just hoping it's gonna work out. I'm gonna plug in the original equation to make sure that we get the same solution, okay? So I've got -1 divided by, where is it? Divided by 2 is less than or equal to, and then I'm going to put this in brackets just so 4 minus 3x, and it'll show you what it's doing as you go, divided by, just make sure that what you've entered here actually matches what you want it to look like, right? Divided by 5, and then move the cursor up, is less than or equal to 1 divided by 4. Okay, so here, hey, it's saying there's an error. We only support solved double inequalities. Okay, fine. That is so annoying. This is why I should have tried it at home first. It's okay. Trial and error. Well, I guess we can break this down, right? And so what you can do is you can hit this, it's got this little button here, and it'll just tell you that when x is 2.167, right, then all the values less than that of x, right, satisfy this inequality. So if we go back and all the values less than, and so if we convert 11 over 12 to a fraction, we get 0.91666. But then remember, the inequality that we're looking for, or looking at right now in Desmos, it got switched over, so it's 13 divided by 6, 2.1666666, which they've rounded to 2.167. Right? And then if we have, you can add another, by just hitting down here, the enter, you can enter another one. And so if we do the same thing, 4 minus 3x divided by 5 is less than or equal to 1 over 4. You can kind of manhandle it this way and say, well, then if I click here, 0.917, which is what we found. Notice that the overlap, we can look at the overlap, and that's the interval that we want. Right? So pretty fun, right? Really useful to check your work and just make sure that you got the right thing. So I'll start introducing that as we go through these problems. Right? Just kind of, this is solving it algebraically, right? So mathy. Or you can solve it graphically, but it requires you to be able to graph them, right? So it's kind of no, yeah. I might get you to draw straight lines, which is what we're doing in the next section. But besides straight lines, yeah, I'll warn you if you have to, if there's any graphing. But as it stands, no, I don't think so. I don't think. Potentially in the later sections, but yeah, as it stands. Okay. So these inequalities that we solved just now are called linear inequalities because there's just x's, right? There's no x squareds, no x cubes, nothing like that. And so if you go to the next page, we've got nonlinear inequalities. We're only going to go up to x squared, right? So our highest power is going to be to the power of 2 because we talked about the quadratic equation and the quadratic formula last day, right? if we have something like ax squared plus bx plus c, we know how to find the solutions for x, right? And so it's going to be a little bit easier. So where are we here? Nonlinear inequalities are inequalities that look like this. What we'll see is that there's steps for solving nonlinear inequalities. They will involve factoring, but for me, that means just using the quadratic equation, quadratic formula. So a nonlinear equality or nonlinear inequality will have powers of x greater than 1. If it has a power of 1, it's a linear equation or a linear inequality. And so we will focus on quadratic equations, on quadratic, or how about I just say quadratics, right? Ax squared plus bx plus c, right, is a quadratic. Notice that I'm not saying is less than or equal to or is equal to or whatever. Just kind of leaving it open-ended. Right? All quadratics, equations, inequalities, whatever. The reason is because we have the quadratic formula to factor a quadratic equation or inequality. So we can use the quadratic formula to factor a quadratic. The quadratic formula, remember, is x is going to be negative b plus minus the square root of b squared minus 4ac over 2a. And that's from section 1.5. The quadratic equation is my go-to whenever I have to factor something, right? I want to boil it down to a quadratic equation so that I can use the quadratic formula, because it gives me clear answers for what I can factor this thing into. And so what we want to do, if we're solving ax squared plus bx plus c is less than 0, for example, right, then we might have something. Maybe it looks like this, right? Maybe this is my quadratic equation. Okay. If I need this whole thing to be less than 0, well, at this point, this is where it crosses the x-axis, right? And so at these are what we call the roots, right? And that's what the quadratic formula gives us, are the roots, the values of x, where it crosses the x-axis. And so if I need it to be less than 0, well, that's all of these values of x, right? Between here and here. These all give negative values. If I want it to be greater than 0, then I need these values, so these values of x and these values of x. Right? but it all changes at the roots. So remember that these are called the roots. So to solve a nonlinear inequality, what we do is just like we did earlier where we got x on its own and then numbers on the other side, right? What we're going to do now is we're going to move everything to one side so that we can have 0 on the other side, right? Because we know how to find the roots of a quadratic equation, right? And so since we know how to find the roots of a quadratic equation, the first step in solving a nonlinear inequality, the first step in solving a nonlinear inequality is moving all terms to one side and having 0 on the other side. Is moving all terms to one side I'll say leaving 0 on the other side. Then we can use the quadratic equation to find the roots, right? The second step is to find the roots, right, which is just the values of x when it crosses the x-axis, right? Or values of x when y equals 0, right, crosses the x-axis. The third step, right, is we don't necessarily know what this thing looks like, right? We don't know that it looks like that. You can use Desmos and have some idea, but what we do is we make a number line with cutoff points at the roots, right? And then we just check little test points in each of those sections, because between the roots, right? So on this side of the root, they're all going to be positive, right? Between this root and this root, they're all negative. Between this root and infinity, it behaves the same way, so it's all positive. So we use the roots as cutoff points, and then we just pick any value that's in those intervals to make test values to see if we get positive or negative values. Yeah. So the third step, which isn't really going to make a lot of sense until we do one, so I'm headed there. I just want to give you an outline. So the third step is to make a sign chart to find the intervals, potentially multiple, or to find the intervals that satisfy the inequality. Bless you. Bless you. How about we start with something kind of mellow, like maybe 42. So is x squared plus 5x plus 6 is greater than 0. Okay. First step was to move everything over so that we've got all the terms on this side and 0 on this side. We already have that step, so done. Right. That's why I said start mellow. Not have to move anything around this inequality. From here, right, we need to find the roots of this equation, right? And so find the roots. Well, plus minus the square root of b squared minus 4ac over 2a. Let's just make a note here that in our case, a is 1, b is 5, and c is 6. Then we have negative 5 plus minus 5 squared minus 4 times 1 times 6 over 2 times 1. We got negative 5 plus minus, and then 25 minus 24, I'm pretty sure. Oops, 46. It is square root of 1 over 2. Right, the square root of 1 is just 1. And so I have negative 5 plus minus 1 over 2. Okay. Which means we're going to have negative 5 plus 1 over 2 and negative 5 minus 1 over 2, which puts our roots at negative 2, right? Negative 5 plus 1 is negative 4 divided by 2 is 2, negative 2. And negative 5 minus 1 is negative 6 divided by 2, negative 2 and negative 3. Okay. This is useful, right? Because now we can rewrite our original x squared plus 5x plus 6, x squared plus 5x plus 6 is the same as, well, what it's saying is that when x is negative 2, the thing is going to be 0, right? And so we get x plus 2, because we always just do the opposite essentially, right? Times x plus 3. Right. I'm showing you this because I hate factoring. So I like to have just a concrete way to say that, well, because I was able to find this and this here, right, then I can rewrite this as this. And I don't have to think about, well, oh, weird. Okay. I don't now have to think about it has to multiply to this, it has to add to this, right? And so for me, I'd rather put in the work, get actual values. But that said, if you're able to look at this and get to here, you don't need to do that, right? I just want to show you that there is a way that we can just say, nope, I'm just going to put in all my numbers, solve for what the roots are. And what you'll find is if you expand this, right, should end up to this, right? So you can always check your work. So now, this all has to be what? Greater than 0. We know at -2 and -3, at -2, this becomes 0, so it's 0 times something, right, is 0. -3, something times 0 is also 0, right? So we know that at -2 and -3, it's going to cross the x-axis, right? And so if we draw our number line, draw a number line, and maybe what I'll do is I'll move this to the next page because I'm going to need more room here. So if I draw a number line here, then I'm going to have cutoffs at -2 and -3. Yeah.
Couldn't it be the other way around? If -3 should be on the left and -2 should be on the right.
Yes, thank you. I was just testing you guys.
No work either way.
Sort of. But it's going to be harder to visualize. Yeah. Thank you. That would, yeah, it would have been very difficult. Okay, so now what we do is we think about, I'm just going to copy it down here, x plus 2 times x plus 3 has to be greater than 0, right? So now if I move this up, what I can do, the trick that we usually end up using is I just pick some value that's on this side, right? So I have to pick a value in this interval, right? A value in this interval and a value in this interval. And we call those test points. And so we just pick test points because like we saw in that parabola, it's going to behave, so the function is going to behave the same at any point less than -3. Right, and at any point between -3 and -2, and any point beyond -2. Right? So we just need to pick nice, convenient values between here. And so draw a number line and pick test points. Let's pick test points anywhere. Beyond -3, I don't know, let's use something like -5. Between -3 and -2 sounds reasonable, right? So -2.5.
So won't there wouldn't be any values between -3 and -2, right? I mean, there would be negative values, but not, no, never mind. There'd be negative values.
And that's, yeah, you did it. You just fast forward it. And so, and then anything that's greater than -2, I like, whenever I can, I like to pick 0, right? And so here, I know 0's on this side of -2, because that's always nice, right? You can see it easily. But like I said, you can pick any value that's kind of nice in those intervals, but you have to pick a test point in each of the sections. Okay? So now what we're going to do is we're going to take this inequality and evaluate it at each point, at each of the test points. Okay? And so what we're going to do is we're going to have x plus, change colors here. X plus 2 times x plus 3 greater than 0. Negative 5 plus 2 times negative 5 plus 3. Negative 5 plus 2 is negative 3. Times negative 5 plus 3 is negative 2. Negative 3 times negative 2 is going to be positive 6. So this gave me a positive value. What we'll end up doing, because sometimes it's actually more annoying to actually find what these values are, right, and solve for it. Remember how negatives behave? If we've got an even number of negatives, then we're even, right? And so then it's positive. If you've got an odd number of negatives, negative 1 times 2 is negative, right? Negative 1 times negative 1 times negative 1 times 2, 3 negatives, still going to be negative, right? And so what we usually end up doing is we ignore what the values are actually going to be, and because it's easy to look at this and say, that's going to be negative, that's going to be negative, right? Negative times a negative makes a positive. And so either way that you want to do it is fine, right? Or we can say that a negative value times a negative values. A negative value times a negative value is a positive value, right? So you can just think about how it would behave, right? And then you don't have to figure out what the actual value is. But either way, in the negative 3 to negative infinity interval, right? Or negative infinity to negative 3 technically, it's going to be positive, right? Which satisfies the inequality, right? So this section's a go, right? Greater than 0, but it cannot equal 0, right? And so here, if it was at negative 3, it would equal 0. And so if we have to rewrite this interval in interval notation, right, we would say, therefore, negative infinity up to negative, negative 3, round bracket, satisfies the inequality. Satisfies the inequality. Because we want greater than 0, right? Not greater than or equal to. So that's where the round bracket, square bracket is going to come from. It's going to come from the inequality that we're trying to solve. All right, let's do the other two intervals. All right. So now we've got, I always run out of room, but I can cheat and make it a little bit smaller. Cheating, I know. So here, if I've got x plus 2 times x plus 3, it has to be greater than 0. And I'm looking at negative 2.5 plus 2 times negative 2 plus 0.5 plus 3, well, that's going to be equal to, we have to shrink this one too. Negative 2.5 plus 2 puts me at negative 0.5 times negative 2.5 plus 3 puts me at 0.5. Looking at these, right, I've got a negative times a positive, and so negative 0.5 times 0.5 puts me at negative 0.25. And so this is going to be negative or, right, if we just looked at this and said, well, that's going to give me a negative, this is going to give me a positive, which gives me a negative overall. Right, that's not in the interval, or not in the, it doesn't satisfy the inequality. So we leave it out. Time for me to squeeze this up again. There. Then it won't be part of the solution. So all we're doing now is we're trying to figure out which portions of this thing is going to work out, right? And if it doesn't satisfy the inequality, then it won't be part of the solution is all. Right? So if we do the next one, then I'll combine them and show you what the total interval is going to look like. Exactly. So if we want to visualize this, right, it probably looks something like, here I'm at negative 3, here I'm at negative 2. Probably looks something like this, right? Because what we found was that for all the values of x less than negative 3, we get a positive value. For all the values between negative 3 and negative 2, we get negative values right below the x-axis. And then, so presumably, beyond negative 2, greater than negative 2, we're going to be back to positives. And so let's just have a look here. And if we do 0 plus 2 times 0 plus 3, we get 2 times 3 is 6, which is positive. Or same idea. Positive times a positive is going to be a total positive. Coughing fits are the worst. I'm guessing that's what happened. Right, and so now this satisfies the inequality. So therefore, if we have to write this in interval notation, from negative 2 up to positive infinity satisfies the inequality. Satisfies the inequality. So what we can say, if I move this up a little bit here. If we've got, we can use the original or just the x plus 2 times x plus 3, it doesn't matter. So therefore, x plus 2 times x plus 3 greater than 0 has solutions on the interval negative infinity up to, oh, clean that up. Negative infinity up to -3, round bracket, right, because it's not including -3, and then union, right, where we smush them together, so can read it as 4 if we want, and then picking right back up at -2 up to positive infinity. Nice. So a little bit different, right? Because we have to use the sign chart, figure out where it's positive and negative. But as long as you remember that the end goal is to figure out where this thing is true, then that's good. So if we use Desmos, just to show you guys, you can keep your work if you just want to turn off the graph. You can just hit these and they'll just kind of go away. So boop, boop. Then you can keep your work and not delete it. But what was it? It was x squared plus 5x plus 6 is greater than 0. And that's what we found. It's between -3 and -2. Those are out, but everything else satisfies the inequality. Nice. What if we had to do one like 51 or 53 or 52? Remember I promised, oh, did I not copy the, I didn't, oh well. 51 or 52, I'll copy them now. Got it. At first, you're seeing an x times an x times an x, so you know it's going to be x to the power of 3, right? But you don't have to expand them, remember? So that's why I've left 51 and 52 in there, because I said, nope, x to the power of 2, that's the highest thing that I need you to be able to factor, right? This is already factored. So we can say, well, I know 50 for 51, for example, I already know that it's going to cross the x-axis at -2, 1, and 3. Right? So I've already got my number line, -2, 1, 3. They just happen to work out in the order too. So if we do 51 together, we've got x plus 2 times x plus 1 times x minus 3 has to be less than or equal to 0. Ha! Thank you. That would have changed everything. Good. Good thing you guys are awake. Messing up. So I want you to try to make that number line, try to figure out what the sign would be, right? Remember, you are interested in the intervals that make it greater than or equal to 0, right? So still looking for positive values, but inclusive this time of 0. Let you guys have a go. So if I just get started here, trying to catch up to you guys now. First thing I'm going to do is I'm going to draw my number line, right? Because that's where I can skip to because it's already been factored, right? It's in terms of 0. And so I've got cutoff points at -2, 1, and 3. Now, what I'm going to do, maybe I should space these out a little bit more because I was tight for space and now I've got even more. Sorry, you've still got time to work on yours. Take me a while to set my number line up. Still not happy with it, but it's okay. Right? And so now with 3 of these things, right, it's going to be annoying to plug in actual values, right? And so that's when we usually just try to just figure out what the sign of this thing is going to be, because I only care if it's positive or negative, right? I don't care about the actual value of it. And so here, I'm just going to use just the sign of it, right? And so anything less than -2, if I've got -2 or -3 plus 2, so you can pick a test point in your mind, right? -3, for example, right? But then what you have, -3 plus 2 is still going to be negative. -3 minus 1 is also going to be negative. -3 minus 3 is still going to be negative. Negative times a negative times a negative gives me a negative. Right. Looking at something, and so here I'll just make a note that I use -3 in there. And then just for my hypothetical, between -2 and 1 is my favorite 0. Between 1 and 3, picking an easy number, I'm going to pick 2, and then past 3, sure, why not pick 5? Right. Again, it doesn't matter. Giving myself a little bit of guideline here so I don't run over. But again, just using the sign, right? 0 plus 2, I can tell right away is going to be positive. 0 minus 1, I can tell right away is going to be negative. And 0 minus 3, I can tell is going to be negative. A positive times a negative times a negative is going to be positive. Doing the same thing with 2. 2 plus 2 is positive. 2 minus 1 is positive. 2 minus 3 is negative. So overall, I get a negative value, right? Positive times a positive times a negative. And then same thing for 5. but judging by the trend and just kind of knowing that it's going to go from being positive to negative, right? So, I mean, honestly, you could probably say something like, well, if I started at negative, the next one must be positive, the next one must be negative, and it doesn't really matter how many you have, right? You'll want to check to confirm it with a graph on Desmos, maybe, but it's pretty safe, right? Because it'll just kind of go up and down, up and down. And so here, if we use 5 in there, 5 plus 2 is positive, 5 minus 1 is still positive, and 5 minus 3 is still positive. And so I get a positive overall. That means that this is in the this solves the inequality, and this one solves the inequality. So I'll put little green. This one's good, and this one's good. This one and this one, they're not in the inequality, right? Just checking. No, sleeping on the job here. Less than or equal to. That's good. This one's out and this one's out. Just changing things around here. Phew. Otherwise, when we go to check it on Desmos, I would have had to do some backpedaling. Oh, good. All right. The interval, right? The inequality is solved. Therefore, the inequality is solved, or it might make more sense to say it's true on the interval. If we had to rewrite this as in interval notation, right, that first interval is from negative infinity up to -2. Now we need including -2 because we want it to be less than or equal to 0. Okay. So we have to use the square bracket. Union, so joined with the interval between 1 and 3, inclusive on both sides, because 1 makes it 0 and 3 makes it 0, right? Which is still true. And then that's it. Nice. Yeah.
Would it be possible, like, if it was a larger equation, that 2 defining?
Oh yeah. You can have this union, this union, this union, this union, this, right? And so it can just keep going. So you just keep building on the pieces. All right, so let's use Desmos just to see what happens here. Again, might be shooting myself in the foot because I haven't tried it actually. I'm just gonna rewrite it the way it is in the question. So bracket x plus 2, and then bracket again x minus 1 times bracket x minus 3. That all has to be less than or equal to, less than or equal to 0. Looks good, right? So here, bless you. It's not letting me pick. Maybe it's because it's obvious. At -2, and then again between 1 and 3. Phew. Which is what we set. And you can zoom out, but it just gives you the interval. Right. Here, if you get rid of the inequality, it gives you the actual graph, right? But once you give it the, has to be less than or equal to 0, it'll just give you the intervals that make that happen. Right? So it gets rid of the graph. But from here, we can see where it's positive and where it's negative too, right? And then it looks like we can click these dots, fill them in. Cool. All right. So at the bottom of the page, yeah, sorry. Yes. More? This part? Give you there. I'll let you see what you need. The bottom of the page has the optional absolute value inequalities. Right. I removed those from your quiz, so you don't have to worry about them, but they are pretty fun. But like I said, it won't be tested, so it's purely optional. So you have the material there, but we're not going to go through them. So we do want to talk about lines, section 1.10. So section 1.10, oh, battery everywhere. Pen's running out, laptop's running out. Section 1.10 is on lines, right? So I'm gonna skip back and forth. But so now we're gonna be drawing straight lines and just talking about the slope and the intercept, right? So if I say y equals mx plus b, you've probably heard something like that before, right? That's a linear equation. And so let me know when you're all good. Cool. So if we go into, I'll start a new page of notes. Section 1.10 is on lines. Section 110, because I've shown you how to use Desmos to graph stuff, which is 111, 110 will be the last section in chapter 1 for us. Which means that all the chapter 1 quizzes are due a week from now, right, on January 31st. So, lines. If I say something like y equals mx plus b, we've probably seen something like that before, right? And so this is the equation of a line. Where whatever is attached to the x is the slope, and whatever's on its own is the y-intercept. Oops. The slope is going to be the rise over run, right? And so if we have a graph, then usually it's kind of easier to tell what the slope is going to be, right? Because we can look at the change in x over the change in y. But what we'll want to do is just given 2 points, we'll be able to find the slope between those two, right? And so if we have a setup like this, and we've got just any line here, to find the slope of it, we can pick any value of x, let's call it x1, and another point, call it x2. x1 is going to map back to y1 on the y-axis, right? We're just using generic notation here. And x2, if I extend this line a little bit, x2 is going to map back to y2. If we want the rise, this distance here is the rise. If I just want to talk about how to calculate the rise, right? The rise is just going to be a distance. And because this value is bigger than this value, right, I'm going to do y2 minus y1. Right? And so I'm going to say that the rise is y2 minus y1, whatever it is. This distance is the run, right? And so the run, same idea. If I just want the distance between x1 and x2, then I'd have to do x2 minus x1, right? So the run is x2 minus x1. So in general, right, the slope is the rise over the run, which we can replace with, right, in terms of the y's and the x's, y2 minus y1 over x2 minus x1. It actually doesn't matter which point we use as x1 and x2, right? They're kind of arbitrary here. And so if we have a look at the examples or the questions, oops, not 1.8, but 110. Copy. One thing that we could do if we're given these points, and the P's and the Q's are just giving names to these points, right? But in general, right, a point is x comma y. And so here, Px comma y says P is the point at x, y. So we could draw these on a graph and actually look at the rise over run. But if we went for something like maybe number 14, where we've got P is 4, 3, and Q is 1, -1. Instead of mapping these out, I'm just going to call P, instead of 4, 3, I'm going to replace it with x1, x2, or x1, y1. Q is going to be y1 or x2, y2. Right? And so here, think of this as P is x1, y1, and Q is x2, y2. Ugh. Because I just find it's too much work to have to think about which one would be on the other end, right? And we don't actually need to, because we're going to get negatives and then they're going to cancel anyways. So if we do that, then the slope is y2 minus y1 over x2 minus x1. Which for us is going to be, okay, here's where I need to keep my wits about me, really. -1 minus 3 over 1 minus 4. Oh. So here, I'm getting -4 over -3. But that's going to be positive, right? And so now I get just 4 over 3. Yeah?
know the positive distance is the negative on the top.
Mhm. Now, the thing is that we're allowed to have positive, negative slopes of 0, right? So some options for our slopes. Positive slope is a slope that goes like this, right? So if it's a positive value like we had here, it's an upward slope, right? And if it's downwards like this, we say it's a negative slope. If you've got a straight across horizontal line, there's no slope, right? You can argue that because if the slope is rise over run, but the rise is 0, you've got 0 over however much you want, it's always just going to be 0, right? And so no slope, here the slope is 0, oh sorry, 0 slope, 0 slope, no slope. Here, if you think about the slope, right, if it's a straight vertical line, then the slope is rise over run. The rise is however big you want it to be, but the run is 0. If we're dividing by 0, that doesn't exist, right? And so no slope. Yeah. So that's just how they all behave. Yeah. We're going to have 2 ways of finding the equation of a line, right? Or defining the equation of a line if you want. The slope-intercept form requires that we know the slope and that we know the y-intercept, right? Y equals mx plus b is the slope-intercept form because we need b is the y-intercept and m is the slope. Okay? I want you to start just defaulting to the point slope form of a line, which says that I don't need to have that specific point of the y-intercept. I can actually have any point that's supposed to be on this line, right? And solve for the equation. And so we can use either the intercept, or sorry, I think it's called the slope intercept. Oh, let's mix them up. The slope intercept form of a line, right? Y equals mx plus b. Just convince yourself, right? You need the slope and you need the intercept, so it's the slope intercept form. Or the point slope form of a line to solve for a linear equation. Should we go that far and call it that? Linear means straight line, right? A straight line equation. And so a point slope form says that we have y minus y1 is m times x minus x1, right? Put a box around that, right? Where x1, y1, right? They're not the same as for the slope that we just used, right? They're just general notation. So where x1, y1 is any point that we know on the line. Is any point that we know on the line. Instead of the very specific having to know the y-intercept. Right? So that's why we use the point slope, because then we can use any point, right? What I want you to notice is that the y-intercept is the point when x is 0, y is b. Try to make a nicer b, but it's hard. If you plug that into the equation, solve for y, you will end up at y equals mx plus b, right? And so that's why the point slope formula is way more useful, because it can get us to the slope intercept form that we're used to, right? But now we can plug in any point, and as long as we know the slope, we can find the equation of this line. Yeah. One thing that's kind of fun about straight lines is, in order to graph a straight line, you only need to know 2 points on the line, right? And then you can connect those points. You use a straight edge. So got my package of gum or whatever, right? And so you connect those 2 points, draw the line, extend the line, and then you're good to go, right? Ugh. Don't look. Nasty. All my stuff. Right, and so to draw a straight line, we only need to know 2 points on that line. We only need to know 2 points on the line, right? If we plot them, we can connect them and extend the line, and then we've got our line, right? Because the straight line, doesn't matter what your value of x is, we're able to figure out what our y's are. Right? So if we plot them, and connect the points and extend the line, we have drawn the entire line. I'll put entire in kind of air quotes here. Straight lines go on from negative infinity to positive infinity, right? So what I mean by entire is for the section that you're looking at, right? Entire line. How about we do example or question 28? I had to squish it, but you guys have it. So 28 says that it has to go through the point -3, -5, and the slope is -7/2. Right. I picked a hard one right away. Okay. So if we've got the point slope form, we've got y minus y1 is m times x minus x1. Right. -3 is our x1 and -5 is our y1. And so we get y minus -5 is the slope -7/2 times x minus -3. Keeping track of your negatives. Right. We get y plus 5 is -7/2 times x plus 3. I can expand this in, right? So y plus 5 is -7x/2 minus 21/2. right? -7 times 3 is -21, and then over 2. And then I get y is moving that 5 over, right? I have to subtract 5 from both sides. -7x over 2 minus 21 over 2 minus 5. In order to combine this -21 over 2 and the negative and the minus 5, I have to get a common denominator. Yeah. Subtract 5. Oh yeah, but multiply by 5 over 5. Or sorry, 2 over 2. Yeah. What was your question? Bringing it in here. So I'm multiplying by x. Gets me -7x over 2, if I want to write it like that. I could have put just the -7 over 2 times x. That's fine. Yeah. Good. So then here, I get y is -7x over 2 minus 21 over 2 minus 5 times 2 over 2. Because I'm very nearly out of time here. I'm going to keep going. Y is -7x over 2 minus 21 over 2 minus 10 over 2. We're so close. -21 minus 10, right? You want to be careful with your negatives. That's right. Y is -7x over 2 minus 31 over 2. And as far as I know, there's no simpler way to write that, so I'm just going to leave it. So the slope, -7 over 2, the y-intercept, -31 over 2. Nice work, guys. Nice work. Any questions? No? All right. Then that's chapter 1, done and dusted. See you guys on Tuesday. And have a good weekend. Thank you. I'm gonna stop this here. Oh, make sure. Good.